That's me, I guess. Yeah. All right. So that nice introduction to Axion searching. I was involved in the initial deployment of quantum squeezing in the Axion search. And that was really an exciting moment for me, someone who kind of likes quantum technology, who's enthusiastic about the idea that quantum enhanced sensing should have impacts and consequence today, not just in some glorious future. And the fact that the Axion search was an example of an experiment that would kind of benefit immediately from these notions of quantum enhanced sensing was very exciting. And so the highly technical slide, which I began my talk with, here just is meant to illustrate the fact that in the end, the Axion haloscope, that sort of cylinder, it is affected by two sources of noise, one of which is just associated with the fact that it's a piece of copper and it is lossy. And you will do as well with that as you can. But there's a second source of noise really associated with the fact that you want to measure the state of that cavity by punching a hole in it and letting the microwave fields come out. And it is that second source of noise that you have access to as a kind of quantum engineer. You say, rather than letting that limit the bandwidth over which my Axion haloscope would be sensitive as I tune it through frequency, looking for a little tiny peak in the noise density, which would be my Axion, and waiting to integrate that noise down, the bandwidth over which I am sensitive is really limited precisely by that noise that you introduce when you punch a hole in the cavity. And it is that noise that you can then suppress, increasing the bandwidth. Now, we'll go to the next slide. Good. As excited as I was, and as kind of fun as it was to increase the scan rate of an Axion haloscope faster than it would have scanned if operated at the quantum limit, if we just accepted the vacuum fluctuations associated with that measurement noise, we benefited by about a factor of 2 from the quantum enhanced sensing. 2 is nice, 10 would be better. And so the next idea that we're working on really kind of stays in the vein of thinking about how you engineer the quantum noise to help you and not hurt you. But the details of which really are intended to move beyond the idea of generating a microwave squeeze state in one location, piping it down into the Axion sensitive cavity, having it bounce off and reach its measurement. The idea is now really to create a direct interaction between an Axion sensitive cavity and some other resonant mode. And in that process, you can create a 2-mode entangled state between those 2 resonant modes. And at the same time, create a kind of stabilizing interaction that allows you to have kind of continuous monitoring of one of the cavity's modes and one of the quadratures of that mode without the measurement back action influencing that. That's the so-called quantum non-demolition interaction. And if we can engineer that, then we have kind of benefited in the sense that we won't have as much loss or diminution of the quantum enhancement associated with transporting the fields through non-reciprocal elements like circulators. That's the basic idea. The progress on that so far, if we go to the next slide, is that we can kind of make a toy version of that experiment and demonstrate the kind of enhanced bandwidth without added noise that would give us maybe an 8 times speed up over the quantum limit. So improving sort of 2 times to 8 times. But that's in the toy experiment, and the real research in the group right now is figuring out how to get all the details just right to deploy it in the Axion apparatus. All right, I think that's about my time. Okay, very good. I see nodding, nervous nodding. No,
Thanks, Konrad.